This video is about slicing and the definite integral and how these concepts can be used to compute area, volume, and several other applications. This video is intended to be an introduction to applications of integration. We can use definite integrals to compute quantities where the components are not constant. For example, in Calculus 1, we computed the area under a curve using a Riemann sum, where we subdivide the interval from a to b into n equal intervals, each of width delta x, where delta x is b minus a over n, and then using a value of x in each subinterval, we compute the height of each rectangle by plugging it into the function. We add up all of these areas to get an estimate of the area under the curve. The bigger the value of n, the number of rectangles, the better the estimate is. So to get the total actual area, we let n go to infinity, which means that delta x, the width of each rectangle, will approach 0. And then the definite integral is the limit as n approaches infinity of this Riemann sum, which is just written as the integral from a to b of f of x dx. Delta x becomes dx in the definite integral, and f of xi becomes f of x because we are saying that the integral is considering all values of x between a and b. We can simplify this process a little bit by considering a representative slice at a given x star. So we'll choose an x star between a and b, and we'll just look at that one representative rectangle. But knowing in the background that we're actually adding up all of the rectangles and then letting n go to infinity. We'll call this representative rectangle a slice of the area. So the area of this slice is going to be the height times the width. So the height is f of x star, and the width is delta x. And then we'll just go straight to writing the total area as the definite integral from a to b of f of x dx. There are many, many applications to this slicing idea. Not only area, but we can compute volume this way. We can also compute arc length, surface area, and various physical applications such as mass, work, and hydrostatic force. In this video, we will introduce volume, arc length, work, and hydrostatic force, giving the basic idea, though in many cases you will need to look to other sources for more details and examples. So the procedure is, we're going to slice a quantity, either area, volume, and so on, into n pieces having constant components. We'll add up those slices to get an estimate of the quantity. We'll take the limit of the sum as n goes to infinity to get the actual quantity, and that's the definite integral. Or, using our simplified process, a representative slice at x equals x star has thickness delta x, where x is the independent variable in the problem. We'll find a formula for the quantity for our representative slice at x equals x star. For this, it's a really good idea to draw a picture and choose a coordinate system that makes sense for the problem. And then we'll turn the formula for the slice into a definite integral to get the total quantity. So our next example is calculating the volume of a solid using cross-sectional slices. In this picture, you can see that we have a solid that's being cut by a plane. When we do this, we get a slice of the solid. And the shape that we get is called the cross section. This slice actually has a little bit of thickness to it. So we can imagine that if we wanted to find the volume of this entire solid from x equals a to x equals b, that we could choose an arbitrary representative value in between called x star, and then this slice has thickness delta x. The volume of this slice, now maybe I'll draw it in a little bit of with a little bit of thickness here. Okay, so imagine that this is a slice with a little bit of thickness, and the thickness is delta x. Then the volume of this slice is going to be the cross-sectional area. So whatever this area is at x star multiplied by delta x is going to give us the volume of that slice. And that will become a definite integral. So the total volume of the solid from x equals a to x equals b is the definite integral from a to b of a of x dx. Here we come to a concept check. Pause and explore. I urge you to pause the video and try to work out the answer for yourself before continuing. We have a 6-foot long air duct, and the only thing we know about it is that it has cross-sectional area A of x equals 4 pi x squared square feet when sliced perpendicularly at a distance of x feet from one end. Find the volume of the duct. Pause the video and come back when you're ready. Okay, so I've just drawn a sketch. I don't know what this duct looks like, but I've just drawn a blobby solid from x equals 0 to x equals 6. And then at a representative point in between, I've labeled this with x star. And at this x star, I've drawn a slice. The volume of the slice is the cross-sectional area times delta x. And we are given a formula for the cross-sectional area. So at x star, the cross-sectional area is 4 pi x star squared. So the volume of the slice there is going to be 4 pi x star squared delta x. So the total volume is the integral from 0 to 6 of 4 pi x squared dx. Then we can evaluate the integral. 4 pi is a constant multiple, and then an antiderivative of x squared is 1/3 x cubed. We evaluate from 0 to 6, and we should get 288 pi, which is approximately 904.78 cubic feet. This is the total volume of the air duct. There are many, many other applications of slicing. Here are 3 more that we will look at in this video: arc length, work, and hydrostatic force. We will only talk about the basic ideas of each. You'll have to look to other sources for details and examples. But I just want to emphasize, rather than memorizing a bunch of integral formulas, it's much better to be able to understand slicing and how we get from the basic formula to a definite integral using the concept of slicing. First, we start with arc length. So our goal is to find the length of a curve f of x from x equals a to x equals b. One way to tackle this problem is to subdivide the interval from a to b into subintervals, and for each subinterval, draw a line segment from the point on the curve at the beginning to the point on the curve at the end, and add up all of these straight line segments, which we can do using distance formula, otherwise known as Pythagorean theorem, and that will form an estimate of the arc length. The more subdivisions we use, the closer and closer this straight line estimate will become to the actual arc length. So in the limit, we will get a definite integral, which will tell us the exact arc length. Now it turns out that if we pick a representative x star between a and b, and we look at the segment formed by the points at x star, the length of that segment is going to be the square root of 1 plus f prime of x star, all squared, times delta x, where f prime is the derivative of f. This formula comes about from the Pythagorean theorem and the mean value theorem, but you'll have to look to other sources for details. But once we know this, then the total length of the curve from a to b is going to be the integral from a to b of the square root of 1 plus f prime of x all squared dx. This formula only works on curves where the derivative is defined for the entire interval from a to b. And that's another detail that is covered in other sources. Next, we have work, which is the product of the force applied to an object times the distance traveled by the object. If these quantities are constant, then all we have to do is multiply to get the answer. For example, if I have a book that weighs 20 newtons and I lift it 2 meters, then the work done is 20 times 2, which is 40 Newton meters, otherwise known as joules. However, if the force and or the distance is not constant, then we will need to slice to get the work done. For example, the work done to stretch or compress a spring. A spring has a natural equilibrium length, which we call x equals 0. If we compress the spring, then we are shrinking the length of the spring by a value of x, which is a negative value. Or if we stretch the spring, then we are stretching a spring by x units, where x is positive. The further we stretch the spring, the greater the force we will need to apply, since a spring will become harder and harder to stretch the further from equilibrium we go. So to calculate the work done to stretch a spring from x equals a to x equals b, then the force is non-constant. So if we let capital F of x star denote the force required to keep the spring stretched a distance of x star away from equilibrium, actually this is x star, this distance here. So if we consider this to be the origin, then this value of x is x star. We're going to slice this work, which means we are applying a force capital F of x star, and we are stretching this spring just a little bit. And by just a little bit, I mean delta x. So this is an estimate of the work done to stretch this spring from x star to x star plus delta x. So the work done to stretch this slice is capital F of x star times delta x. And therefore, the total work done is the integral from a to b of capital F of x dx. Another application of work is the work required to pump water out of a tank. So we've got a tank full of water. We're trying to pump the water out of the tank. And as we do so, we've got the water at the top that weighs a certain amount. So in order to pump the water up, we're going to have to apply a force in the opposite direction equal to the weight of that water. And we're going to have to lift it up to where the water is going to come out. The amount of water is going to affect the force that we need to apply, and how far we need to pump it is also going to vary. So we're going to estimate the work done by considering slices of water and how much work it takes to pump that slice of water out of the tank. So at x star, this is where we're going to need a coordinate system. We have several choices. Let's suppose our tank is, say, 20 feet deep. We could choose a coordinate system where the top of the tank is considered 0, and the bottom then would be considered x equals 20. And then maybe our pump is at a distance of 3 feet from the top of the tank. So then the exit for the water is going to be at -3. That's one possible choice. Another possible choice is we could let 0 be at the bottom of the tank, and then at the top of the tank would be 20, and then at the top of where the pump is, that would be 23. Yet another option, we could decide that where the water is going to come out, that could be 0, and then the top of the tank would be at 3, and then the bottom of the tank would be at 23. These choices will affect how we set up our integral, but the answer should come out the same regardless of what coordinate system we choose. Since we need to integrate over the entire height of the tank, and since integrals will be easier to compute if one of the coordinates is 0, let's just go ahead and set our coordinates so that the bottom of the tank is 0, the top of the tank is 20, and the top of the pump is 23. The force required to lift this slice of water is going to be the volume of the water times the weight density of water. In the imperial system, this is the one that has feet and inches and pounds, the weight density of water is 62.5 pounds per cubic foot. So we'll be multiplying that weight density by the volume of the slice. The volume of the slice will be the cross-sectional area of the slice times delta x. The distance component also varies with x star. The distance that the slice of water has to travel I'm calling P of x star. And we can see, using this coordinate system that we have set up, that this distance is going to be 23 minus x star, because this distance is x star, and this distance is 23. So when we take 23 and take away x star, we get 23 minus x star. So for the slice, the work done to pump the water a distance of P of x star is omega, which is 62.5, times P of x star times A of x star delta x. This is the force times the distance. And so now all we have to do is turn this into a definite integral. The total work done to pump all the water out of the tank is going to be omega, which is a constant, times the integral from a to b of P of x times A of x dx. Again, I recommend that you not memorize this formula, but rather use the concept of slicing and draw a picture so that you can use the fact that work is force times distance to work out this formula for yourself for each problem. In this case, our A will be 0 and our B will be 20, and our P of x will be 23 minus x. So just filling in all of the details that we have, omega is 62.5. Then we're integrating from 0 to 20, because that's where the water is. P of x is 23 minus x. And then A of x is unknown because we don't know anything more about the shape of this tank. dx. Lastly, we're going to talk about hydrostatic force on a surface. If you've taken a physics class, you may know that the hydrostatic force on a surface that is submerged is the weight density of the fluid times the area of the surface times the depth. Everything is constant as long as the surface is horizontal in the water or the fluid, because it is then of uniform depth. But if the surface is positioned vertically in the fluid, then the depth will vary. So we can slice to get the hydrostatic force on a slice of the surface and then integrate. So the area at the depth x star is going to be the width at x star times delta x. The depth at x star we will denote by S of x star. This picture is assuming that the surface of the fluid is right up here at the top. So in practice, we would set up the problem by determining a coordinate system that made sense for the problem. We could use 0 at the surface of the fluid and work down from there. Or in this case, this is a round plate, and I might consider making 0 the center of the plate, because that will make it easier to compute the width using geometry. But that's for another video. We've worked out the area, and we've worked out the depth. So the hydrostatic force at x star for this slice is going to be omega, the weight density of the fluid, times the depth at x star, times the width at x star times delta x. So the total hydrostatic force is going to be omega times the integral from a to b of s of x times w of x dx. In summary, we can use slicing to set up a definite integral for many types of quantities. So to compute the total quantity from x equals a to x equals b, we saw that we could follow this general procedure. We'll write a basic formula for the quantity, assuming all components are constant. For example, work equals force times distance. If a component is not constant for the problem, we'll draw a picture showing a representative slice of what we want to compute. So for example, in the tank problem, let's suppose that our tank is now 30 meters deep. We'll draw our representative slice and label that with x star. We need to choose a coordinate system that makes sense for the problem. So maybe for this problem, just to change things up, I will let 0 be the top of the tank and 30 meters be the bottom. And then let's suppose that the place that the water will be exiting is 2 meters above that. So then this value will be -2. Here's our x star. Then we'll write a formula for the work done for this slice. The volume of the slice is the cross-sectional area, A of x star times delta x, and the weight of that slice is going to be the weight density times that volume. And the distance it has to travel is x star plus 2. Okay, so we developed a formula for the work done on this slice. So then we set up our definite integral. The work done is omega times the integral from 0 to 30. And then we just turn all the x stars into x's. So we've got a of x times x plus 2. And we turn delta x into dx. And there's our integral. I hope you found this video helpful.